If quantum computing gets involved in AI, what are we looking at?
So we're talking about an extremely powerful alliance between software and hardware. The chatbots that are a revolution in software, and then quantum computers, which are a revolution in hardware, when they get together, watch out.
Michio Kaku, being a theoretical physicist and a futurist, often discusses the vast potential and the challenges associated with emerging technologies, including quantum computers.
Now, I'm a scientist. We like to think about things that are creative, new, innovative, things that'll change our perception of the world.
His concerns about quantum computers primarily revolve around their potential impacts on security, privacy, and the social fabric, rather than a fear of the technology itself. Now, how do these computers exactly work? Quantum computers bend the rules. Unlike regular computers, they use qubits that can be 0, 1, or both at once. This mind-blowing ability lets them tackle problems impossible for classical computers.
Quantum computers are powerful enough to survey the entire landscape and give reasonable rebuttals.
Building them is like engineering sci-fi. Qubits are coaxed from exotic materials in near absolute zero temperatures, but the hardware is just the start. Special instructions like quantum gates are needed to manipulate qubits and perform calculations. These delicate systems are prone to errors. Scientists use complex protocols to act like quantum mechanics ninjas, constantly fixing mistakes without disrupting the qubit state.
And just remember that where do correct ideas come from? Correct ideas come from interaction with incorrect ideas.
Keeping them stable requires extreme measures. Dilution refrigerators, essentially superpowered freezers, are used to minimize noise. It's like building a computer and sticking it in a giant vat of liquid helium. While the mind-bending potential of qubits existing in multiple states simultaneously promises to revolutionize problem-solving.
Quantum computers are the ultimate computers because they're computing on atoms, and they can do calculations that are far beyond anything that we can calculate with.
Keeping these machines' operational presents a unique challenge: extreme cold. Superconducting qubits, a common type, require temperatures near absolute zero, colder than the depths of space. Enter dilution refrigerators, the unsung heroes of quantum computing. These superpowered freezers constantly whir away, maintaining a frigid environment for the delicate qubits. The downside? They consume energy like a small country, upwards of tens of thousands of watts. But here's the surprising fact. While the calculations themselves might be energy efficient for specific tasks, the supporting infrastructure behind quantum computers comes with a hefty energy cost. Dilution refrigerators and the intricate electronics needed to control and read qubit states are real power guzzlers. So how exactly do these mind-bending qubits translate to mind-blowing speed? Here's where the true magic of quantum computing unfolds. Imagine having 1,000,000 coins spinning in the air, each able to land on heads or tails. A regular computer can only check each coin one by one, but a quantum computer can analyze all the possibilities simultaneously thanks to superposition. This parallel processing power lets them tackle problems in a way that would leave even the most powerful classical computers in the dust. But it's not just about raw power. Quantum computers also have special algorithms designed to exploit the unique properties of qubits. Take searching a massive unsorted database for a specific item. A classical computer would have to check each entry one by one, but a quantum algorithm could find it in a fraction of the time.
We have to get used to the idea that quantum computers introduces a whole new way of looking at reality.
This dramatic speed-up paves the way for tackling challenges in fields like medicine, materials science, and artificial intelligence, where complex simulations and calculations are currently bottlenecked by classical computing. Now, the realm of digital security is on the cusp of a significant transformation, courtesy of the advancements in quantum computing. This leap forward in computational capabilities brings into sharp relief the vulnerabilities inherent in our current cryptographic systems. Traditionally, the bedrock of digital security, public key cryptography, finds itself particularly exposed. This cryptographic method, which secures everything from our emails to financial transactions, relies on mathematical challenges such as the factoring of large prime numbers, and solving discrete logarithm problems. These tasks, though straightforward for computers to perform in one direction, are exceedingly difficult to reverse without the correct key, making them secure against attacks from classical computers. However, this security is predicated on the limitations of classical computing. Enter the world of quantum computing, where the rules of the game change entirely. Qubits, they can exist in multiple states simultaneously, allowing quantum computers to perform many calculations at once. This ability poses a direct threat to the foundation of public key cryptography. For instance, RSA encryption, which is reliant on the difficulty of factoring the product of two large prime numbers, could potentially be undone by a quantum computer in seconds or minutes, a task that would take a classical computer thousands of years.
Quantum computers allows us to calculate things that are way beyond our ability to calculate today.
The introduction of Shor's algorithm in 1994 was a pivotal moment, showcasing the potential of quantum computers to solve these heretofore intractable problems at speeds unfathomable to classical machines. This algorithm can efficiently factor large numbers and solve discrete logarithm problems, rendering encryption methods like RSA, Diffie-Hellman, and ECC vulnerable. The implications of this are profound, indicating a pressing need for new cryptographic standards impervious to quantum computing's capabilities. On the flip side of this looming threat is the emergence of quantum cryptography, offering a glimmer of hope in securing communications against the prowess of quantum computing. Quantum key distribution, or QKD for short, a novel approach in this field leverages the very principles of quantum mechanics that threaten current encryption methods to secure communication channels. QKD's security foundation is not computational complexity, but the physical properties of quantum particles. A standout feature of this method is its incorporation of the no-cloning theorem, which states it is impossible to exactly copy an unknown quantum state. This principle ensures that any attempt at eavesdropping can be detected, as interacting with a quantum system to measure it invariably alters its state, thus alerting the communicating parties to the security breach. As we delve deeper into the potential of quantum computing, it's impossible not to marvel at its revolutionary capabilities. This leap forward in computational power promises to unlock solutions to problems that have long remained out of reach for classical computers. Yet, as with any significant technological advancement, the introduction of quantum computing brings with it not just opportunities, but also substantial risks and challenges. These advancements suggest that the day when quantum computers can crack current encryption methods is not a distant future scenario, but an impending reality. However, the implications of this quantum leap extend beyond the technical challenges of upgrading encryption standards. They touch upon the very fabric of digital privacy. The strategy of harvesting data today in the hope of decrypting it tomorrow poses a unique and delayed threat to privacy. Information that is encrypted and considered secure now may, in the future, be laid bare, exposing individuals to a spectrum of risks from identity theft to financial fraud. Continuing our exploration into the quantum realm, let's pivot to another area where its impact is both promising and profoundly unsettling: the financial markets. The advent of quantum computing is set to usher in a new era of opportunities and risks, fundamentally altering the landscape of financial analysis, trading, and the very fabric of digital currencies. Cryptocurrencies, for instance, stand on the front line of this quantum revolution, renowned for their security, which is underpinned by complex cryptographic algorithms like SHA-256 for Bitcoin and ECDSA for Ethereum. These digital currencies rely on the computational impracticality of breaking these cryptographic codes. However, the theoretical prowess of quantum computing threatens to dismantle these cryptographic defenses, opening the door to potential double spending attacks or the unauthorized creation of coins. This isn't just a minor glitch in the system. It's a foundational threat that could undermine the integrity of blockchain technology itself, allowing malicious actors to alter transaction histories or abscond with funds. The mere hint of vulnerability to quantum attacks could shake the very confidence that has buoyed cryptocurrencies, leading to market volatility, plummeting values, and a re-evaluation of digital currencies as secure, decentralized financial instruments. The ripple effects of such a scenario are hard to overstate, potentially reshaping the landscape of digital finance. But the influence of quantum computing extends beyond the realm of cryptocurrencies, promising to redefine financial modeling and prediction. With the ability to process and analyze complex financial systems at speeds and depths unfathomable to classical computers, quantum algorithms could offer unparalleled insights into market trends, risk factors, portfolio optimization, and arbitrage opportunities. This quantum leap in analytical capabilities could transform how we understand and interact with financial markets. However, this quantum advantage doesn't come without its own set of challenges, particularly in terms of market fairness. Imagine a world where a select few have access to quantum computing resources, enabling them to make informed trades based on predictions far ahead of the market curve. Such a scenario would not only disrupt market dynamics, but also raise significant regulatory and ethical questions. The potential for an unfair competitive edge necessitates a rethinking of financial regulations to ensure a level playing field, where quantum-enhanced insights don't undermine the integrity of the markets. Imagine being able to crack the toughest safes online with a brand new kind of computer. That's the fear with quantum computing.
The CIA is very much concerned about it because these quantum computers can crack any known digital code.
These machines use the strange laws of the quantum world to solve problems that would take regular computers years, even centuries. And one of their biggest threats? Our online security. Here's the thing. A lot of the encryption keeping your data safe relies on difficult math problems, like factoring giant numbers so big they'd take a regular computer forever to crack. But quantum computers could zoom through these problems in seconds thanks to something called Shor's algorithm. This is a recipe for disaster. Encryption systems like RSA, which keeps your online shopping and banking info safe, could be wide open. Scary, right? But it's not all doom and gloom. There are other encryption methods like ECC that use different math problems. The trouble is, quantum computers could crack those too with some tweaking. So, what does this mean for our online world? It means we need to prepare for a future where the old ways of encryption might not be enough. Scientists are working on new methods, called quantum-resistant cryptography, to keep our data safe in the age of superpowered computers. The switch won't be easy. It's like upgrading all the locks in your house at once. But it's important. We need to be ready before quantum computers become powerful enough to crack the codes that keep our information hidden. Think of it like the code-breaking breakthroughs of previous war times. Quantum computing could be a game-changer, but this time for cybersecurity. The race is on to develop these machines, and whoever gets there first could have a huge advantage.
So there's a race to see who can get the first quantum computer to put on the marketplace.
It's a complicated situation, but one thing's for sure. The future of online security hinges on outsmarting these superpowered computers. When it comes to quantum computing, IBM has been a real trailblazer. They were there at the beginning, funding research into this mind-blowing technology way back when it was just theoretical ideas. They saw the potential of using the strange rules of the quantum world to build superpowered computers, and they haven't stopped pushing the boundaries ever since. Here's a glimpse into what IBM has done to make quantum computing a reality. First, they invested heavily in the groundwork. They funded research into the basic principles of how quantum computers could work and what kind of problems they might be able to solve. This wasn't just about building a machine, it was about understanding the entirely new way these machines would process information. IBM also realized they couldn't go it alone. Quantum computing is complex and requires experts from many different fields working together. So they teamed up with universities, research labs, and other companies to combine their brainpower. This collaborative approach has been key to making big leaps forward in this rapidly developing field. But IBM wasn't just focused on theory. They knew they needed to build the actual machines to make this a reality. One of their big breakthroughs was developing these things called superconducting qubits. These are the building blocks of quantum computers, and they're like tiny quantum switches that can be flipped on and off. Keeping these qubits stable and working together is super challenging, but IBM has made huge strides in this area. They've also been busy building bigger and better quantum processors. It all started with just a few qubits, but now they're up to machines with over 50 qubits. Each new generation is not only bigger, but also better at handling the delicate quantum calculations. There's a catch though. Quantum computers are error-prone. To make them truly useful, they need a way to fix these errors. IBM is working on quantum error correction, a fancy way of saying they're figuring out how to make these machines more reliable. It's a tough nut to crack, but it's essential for building large-scale quantum computers. Beyond the hardware, IBM is also writing the software for these machines. They're developing quantum algorithms, which are basically special sets of instructions designed to take advantage of a quantum computer's unique abilities. These algorithms could help us solve problems that are impossible for even the most powerful classical computers today. One way IBM is making this quantum knowledge more accessible is through a project called IBM Quantum Experience. It's basically a cloud platform that lets anyone play around with real quantum computers. Pretty cool, right? They've also created open-source software tools called Qiskit, which gives developers a leg up in building quantum programs. Unlike your trusty laptop, quantum computers are built differently. They crunch data using the strange laws of the quantum world, and that means they operate on a whole new level. Let's see how IBM's quantum computers stack up against our everyday machines. First up, energy consumption. Here's the good news. At the quantum level, these machines are pretty frugal. They use qubits, not transistors, and that keeps their energy needs way down compared to classical computers. The flip side is they need super cold temperatures, think close to absolute zero, to function properly. Keeping things that chilly requires a lot of energy, but it's a necessary evil to make the whole quantum magic work. The real benefit of quantum computers comes when they tackle specific problems. Imagine needing to solve a super complex puzzle. A classical computer might take forever, but a quantum computer could zoom through it, using way less energy in the process. This efficiency comes from their ability to do tons of calculations at once, thanks to a special property called superposition. Here's the catch. Quantum computers are still under development. They're not ready to replace your laptop just yet. For everyday tasks, classical computers are still the champ. But for certain problems, like simulating complex molecules or cracking tough encryption codes, quantum computers have the potential to be game changers. It's like having a superpowered tool for specific jobs. Quantum computers are like superpowered research tools, opening doors to incredible discoveries in medicine, materials science, and artificial intelligence. Imagine simulating the building blocks of life or designing new materials with mind-blowing properties. That's the kind of future quantum computing promises. Here's a glimpse of the exciting possibilities. In medicine, quantum computers could accelerate drug discovery by simulating how drugs interact with our bodies on a super detailed level. This could lead to faster development of new treatments and cures. But quantum computing isn't all sunshine and rainbows. There's a flip side to this powerful technology. Because these machines are so good at crunching data, they could also be used to create highly sophisticated weapons systems or even develop new types of threats. Scary, right? The concern is that these technologies could fall into the wrong hands or be developed without proper safeguards. Imagine powerful weapons making decisions on their own, or new diseases emerging from unintended consequences. That's why it's important to carefully consider the ethical and safety implications of quantum computing alongside its potential benefits. Think of it like building a powerful new tool. You can use it to build a house or break things. It depends on your intentions. Quantum computing is the same way. We need to make sure the rules are in place to use this technology for good and avoid any unintended harm. So quantum computing is this super powerful tool, but with great power comes great responsibility, right? That's why we need to think carefully about the ethical and legal implications before we dive headfirst into this new world. Imagine developing a cure for a disease using a quantum computer, but then someone uses the same technology to create a deadly virus. That's the kind of scenario we want to avoid. Here's what needs to happen. First, we need clear guidelines about how to use quantum computing ethically. This means thinking about privacy, security, and how this technology might affect the environment and society as a whole. Basically, we want to make sure the good outweighs the bad. We also need to develop regulations to keep up with the rapid pace of quantum advancements. Think of it like traffic rules for this powerful new technology. These rules need to be flexible enough to adapt as things change, but strong enough to prevent misuse. International cooperation is key here, so everyone's on the same page. Another important piece of the puzzle is transparency. The public needs to understand what's going on with quantum computing, both the good and the potential risks. This way, we can have an informed conversation about how to develop this technology in a way that benefits everyone. Companies like IBM are already thinking about these issues. They're developing quantum computers, but also working with others to explore the ethical implications. It's a good model to follow, kind of like how we developed safety regulations alongside advancements in other powerful technologies. Remember the CRISPR gene editing tool? That's a great example. It has the potential to cure diseases, but it also raises ethical concerns. We need to learn from these situations and make sure quantum computing goes down a responsible path. With careful planning and open communication, we can harness the power of quantum computing for good.